Okay, I have your exams. I posted the exam key a few minutes ago on the Blackboard site, so you can check your answers. I'll release the grades so that it updates basically your grades. There's one set of grades that I don't have transferred over yet, and that is the sapling sets. So I'll move those over because those are a part of your final grade. So by Wednesday, hopefully everything will be up to date. We should have an in-class quiz on Wednesday and then on Friday as well, and that'll end the grade stuff for this semester, except the final. You may have seen that there's one last chapter of sapling problems, which I released, I think, yesterday. They're due by Saturday, I believe, at midnight. And then Chapter 9 I don't normally grade, so I did put the Chapter 9 sapling problems up, but they're practice. So you can do them, not do them. I'll probably end up reassigning those next semester. What else? So we've got that. The video for Wednesday is up. There's a pre-lecture quiz. There'll be one for Friday as well, and I'll release that probably later today. So Wednesday and Friday are both up. Try and do the right quiz, though. I usually try not to put two online quizzes at the same time because then people do the wrong one. But so it's just the first one. Okay.
Will there be in-class?
Yes, Wednesday and Friday, both. And at the end of class, we'll say what Wednesday's is. We've got a lot of reactions that you need to remember for the final, so we might as well have an in-class quiz to kind of make you learn them. I know it's the last week and everybody's kind of quit, but general rule is don't quit until the end of finals, because if you do too early, bad things will happen. Just like paying attention. Probably best to not pay attention after the final exam. But there's only so much I can do. When I got here 20 years ago, the late Dr. Weaver told me, he's like, the last 2 weeks they won't listen to you. And I said, what? What do you mean the last 2 weeks nobody will listen to me? And since I was coming from the Ohio University where nobody listened to me, period, because, scholarship is below Halloween on their list of priorities. I said, well, I guess I'll be used to it then. But all we got is 3 more classes, so. All right. And there are a couple of things that I do want to go over at some point from the last test because there were some things that we need to work on. Okay, but let's finish up our reactions of alkenes. Now, for Wednesday, it's going to be alkynes, and then Friday, it's reactions of alkynes. And one of the reasons why we can kind of go through alkyne reactions relatively quickly is because if we know our reactions of alkenes, which are just one double bond, one pi bond, then the reactions of alkynes are just 2 pi bonds, and so you can do twice as much stuff with a triple bond as you can with a double bond. So if you forgot your reactions of alkenes, which there were a few on the test, but there are also some that are kind of in between, then you need to remember them because they will come back on Wednesday. All right, so here's where we kind of left off last week, whenever we left off last week. I think it was like Monday. So there are some reactions here that aren't electrophilic, where I'm adding something across the double bond, but not necessarily electrophile nucleophile. And a lot of these mechanisms, again, I'm just kind of giving you an idea so you can remember the regioselectivity or the stereoselectivity, but they're not going to be mechanisms that I ask you to do. And the first one was the idea of hydrogenation. So when you're doing hydrogenation, you're going to take an H2 with either palladium or platinum metal, and you're going to add 2 H's across the double bond. And because of the quote-unquote mechanism of this, it is cis. It's 100% cis, but the way we visualize the mechanism is to say, okay, the hydrogen molecules kind of sit on the surface of the metal, and then the double bond approaches, so that, in essence, what I'm doing is, if I think about this double bond, I'm kind of transferring electrons like this. So what I'm going to end up with is a one-step, concerted process. I won't really call it a mechanism because what I'm showing you isn't the real mechanism. I think there's enough evidence that maybe the hydrogen atoms dissociate on the metal surface so that they basically become 2 hydrogen atoms. But neither here nor there, we can view this as being one of those square transition states. So that leads us to adding the hydrogens 100% cis. So we've seen before that when you end up with sort of a square transition state, when you're adding boron and hydrogen, that you always add 100% cis. When you've got a triangular intermediate, it's 100% trans. So that can kind of help you remember the mechanism if you're stuck. But honestly, understanding this mechanism is really difficult because we have to understand how the gas interacts with the metal, and that process is really complicated. People need to know about that process. For instance, in refining, if they're taking natural gas and they're trying to do something with it with a catalyst, but understanding the surface and gas interactions is really complicated. So it's not the mechanism, but it helps us. Remember, it's 100% cis. Okay, and then we just briefly started to talk about carbenes. So a carbene, again, is a carbon with 2 electrons. It shares 6 electrons. It's very unstable. There's no charge. And so the carbene basically will take its pair of electrons, form a carbon-carbon bond, and then the double bond will come out like that, so that we'll make a transition state that kind of looks like this. And so the CH2 ends up adding to one side of the double bond or the other to form the cyclopropane. And this reaction then, if I had, for instance, the trans, then I would end up with the trans cyclopropane, because the CH2 adds in one concerted mechanism. And so in that case, this reaction would be classified as being what?
Stereospecific.
It's going to be stereospecific, right? Because if I trans gives trans, if I change this to cis, if I change the starting reactant to cis, it would become cis product. So it's like the epoxidation. It's like forming the epoxide. So those were our 2 stereospecific examples. So the carbenes. The only question is, how do we make a carbene? And to make a carbene, there's a couple of ways. So we talked a little bit about diazomethane, the idea of taking CH2N2. If you heat this or apply ultraviolet light to it, it splits off the nitrogen gas and makes the carbene. And then that carbene can add, so we can make a pure cyclopropane from diazomethane. or if we don't like the danger that's posed by that, because if we're not careful, we're making gas and it can explode, so we have to, that's a rather, I don't know that's dangerous, but it's one you have to be cautious with. You can also react diiodomethane with a zinc and copper metal mixture, and that will form what's called a carbenoid, which basically means that the CH2 is stabilized by the zinc metal. Same CH2 will add to the double bond. So if you just want to make a cyclopropane with the CH2, your choices are diisomethane or what's called the Simmons-Smith reaction. Either of those two would make a cyclopropane, a straight cyclopropane with the CH2. The other way to make the to add a carbene, but not a carbene with CH2, but with two bromines, is to take this molecule, which is called bromoform, and the potassium hydroxide will be protonate as hydrogen. That will then lose a Br minus to form the carbene with two bromines, and so you can make a cyclopropane ring with two bromines attached to it. So honestly, the diazomethane, I think, is the preferred method, followed by the Simmons-Smith carbenoid. But this will work if you wanted two bromines there. So why would you want to make a cyclopropane ring? There's lots of natural products, meaning products that we can isolate from natural sources that have cyclopropane rings. We talked about the idea earlier that if you had a cyclopropane ring, that the sp3 bonds, they won't be able to line up perfectly head to head, because this is a 60-degree angle, and these are all 109.5-degree angles, so there's no way that the triangle, that the orbitals can line up perfectly head to head. So they have to kind of skew, and that makes the triangle less stable. But it doesn't mean that it doesn't exist. So there's lots of natural products that have one cyclopropane ring, or they might have, I've seen them where they have a whole series of them attached together. They're usually made by like exotic creatures like sea urchins and corals and stuff like that that you find like in Hawaii. So there's a lot of people whose job, well, used to be, a lot of people whose jobs were to find natural products that had unique structures, and so they would spend a lot of time scuba diving in exotic Hawaii and Australia and New Zealand and find sea creatures, pull them out, and then sadly the sea creatures found themselves in a blender, and they would extract all the compounds from the sea creature, and they find some good ones. Good ones meaning some with maybe anti-tumor activity, or that they had anti-cancer activity. And then the question is, you can't go around killing all the sea creatures to get a tiny bit of drug. You got to figure out how to make it. If your drug has a cyclopropane ring in it, you got to make it. This is a way to make it. So that actually is where a lot of these compounds are found. And that's actually was very common in, I think, the 70s. There was a drug that came from the bark of the California yew tree. And of course, I can't remember its name right now. Taxol. Taxol back 20 years ago was in experimental trials for ovarian cancer. But the only place you could find it naturally was in the California yew tree bark, which is a tree that grows in Oregon, not California. And it's not a big tree, it's a little scrubby tree, and you had to rip the bark off of it and do lots of extractions to get the Taxol out of it. But once they got it, then they found it had anti-tumor activity for ovarian cancer and a lot of other cancers now, but you have to synthesize it. And so it has like 20 chiral centers in it. They all have to be right. So, if you find a natural drug or natural product, you have to somehow be able to make it, which is why we're going to learn all the reactions that we have learned and will learn in the next couple days, as well as the entire next semester. It's because those reactions are what people are using to make those molecules. Because there wasn't enough California yew bark to make enough Taxol to treat a couple of patients, let alone all the ones that they wanted to. So that's why you can say, who cares if I can make a cyclopropane ring? Well, you do if you're trying to make a target molecule that has some anti-whatever activity. So as far as these kinds of reactions go, they are stereospecific. So these reagents are one of a kind. They are the only reagents that we will use this semester and this year. So if you're thinking about, okay, well, I'm starting to get a lot of reagents that I need to learn for the final exam. You know, how am I going to manage that? A lot of times people will write 3x5 cards out, and they'll put like a molecule and then the reactant, and on the back of the 3x5 card write the product. So that way if you start going through them, you can put it down and write the structure out and then flip it over and see if you were right. But there's some reagents that we use that do different things. Hydrogen peroxide is one. It shows up in a couple of different places. But these reagents, the diazomethane, the Simmons-Smith, or this CH3BR3, KOH, only one reaction they do. So when you see them, you got to think cyclopropane. That's what I'm making. Just like when you see tertiary butoxide, what should you think? E2. Just like when you see NH2 minus, you should think E2. Oh, Wednesday we'll change that a little bit because there's one more NH2 reaction. But it's still NH2 reacting as a base. So if I looked at this, I would say, well, okay, I'm going to add my C with my two bromines. So I'm going to make my cyclopropane ring. And then if I'm looking at this is a CH3. For instance, for this one, I would say, well, I know that the stereochemistry is preserved, so the methyl groups are trans. That means that the product is trans. So the methyl groups go trans. So you have to begin to kind of think that way in terms of the reagents. And for the reagents that only do one thing, it's going to be hopefully a little bit easier. For other reagents that do more than one thing, it's going to depend on the context of where they're at. Okay? So we can make cyclopropane rings. Now, there are other things that I can add across the double bond. One of the things that I can do is add two OHs. I've added one OH with an H. So I've added H and OH 3 different ways. Right? Markovnikov 50-50, Markovnikov 100% trans, and anti-Markovnikov 100% cis. Actually 4 ways. Because if I make an epoxide, remember if I make an epoxide and I open up the epoxide with acid and water, I've also added 2 OHs trans. That's a good reaction to remember. The idea that if we take a double bond and we convert it to the epoxide, and then we add H plus H2O to it, we end up the net result being 2 OHs added across the double bond, 100% trans. The reason I'll show you that again is because here we have a method, let's say, that you're thinking about, well, okay, I don't want to add two OHs trans, I want to add them cis. How do I do it? Well, here's a couple of ways to do that. In one step, there is no one-step method to add two OHs trans. That's why we have to go through the epoxide. But if I'm looking at adding two OHs cis, that's called Cis-Hydroxylation. And there's two reagents. I can use osmium tetroxide and hydrogen peroxide, or I can add KMNO4 and hydroxide. Now, H2O2, we've done things with H2O2. It's hydroboration oxidation. BH3, H2O2. So the H2O2 oxidizes molecules. What does oxidation mean? In organic chemistry, it means you've added oxygen. So that's what peroxide does, is it oxidizes stuff. In this case, I'm adding two OHs, so it's an oxidation reaction. Osmium tetroxide is a catalyst for this reaction. So we use a little bit of osmium tetroxide, usually less than 1 mole, if I had a mole of alkene, and then we add a large excess of hydrogen peroxide. KMNO4 and base. KMNO4, we're going to find does different things. In this case, KMNO4 is basic. So it cis-hydroxylates. KMNO4, dirt cheap. You know, it's the purple solution that you may have done titrations with last semester, or last whenever in general chemistry lab. But KMNO4 and base cis-hydroxylates. So, what about the stereo and regioselectivity? Something that we do need to work on. And we will do that. If not today, we'll do it by the end of the week. We'll do some more regio and stereo selectivities. But can the reaction be regioselective? No. It can't be regioselective because I'm adding two of the same group across the double bond. So there's no Markovnikov. So anytime, again, your reagent is symmetrical or your alkene is symmetrical, it can't be regioselective. Can it be stereoselective? Well, two things we need for a reaction to be stereoselective. We need to make two chiral centers in the product, and we needed to have added the groups 100% cis or trans. So in this case, this reaction could be stereoselective if we made two chiral centers, because we'll always add the OHs 100% cis. Okay. So these two reactions are a contrast to the epoxide opening. It's the opposite. And is there a mechanism for this that you have to remember? No. But I will show you the mechanism sort of to help you remember why the reaction is cis. So here's just a restatement of that. If we take KMNO4 and base, we're going to make what's called a diol, a dialcohol. And in particular, this is going to be called a cis diol because it's cis. We only see the cis and the trans if we use a cyclohexene. Then we'll see that we've added the two OHs, 100% cis and 0% trans. So again, this is that reaction would be stereoselective. This one would be stereoselective. Why? Because I have two well, let me go back to the rules I just used. How many chiral centers are in this molecule? Did I add the reagent 100%? Yes. So therefore, this is stereoselective. If you want to think of it in a more broad sense, there's two possible products I could form, cis and trans. Did the reaction select one? Yes, 100% cis. And remember, selectivity is such that there's no difference between 51% and 100%. All right, mechanism. Okay, so here's kind of the mechanism by which this reaction goes. And it shows you the arrows of how things are moving. In this mechanism, what I can see is that the manganese is gaining electrons, right? This is gaining electrons. So the manganese then would be undergoing gain electrons as reduction. So the manganese is being reduced, which means that the other compound is being oxidized, which is the double bond. So in organic, while we say, okay, if you gain oxygens, you're being oxidized, it all boils down to the general chemistry rule about, well, gain electrons is reduction, and then up here, if I lost electrons, that would be oxidation. So you can look, if you look hard enough, you'll find the electron movements match up with general chemistry, but you have to determine oxidation numbers, and we don't normally do that. So manganese reduced, the double bond oxidized. Notice that in this pair of electrons, I'm making a 5-member transition state. And the product has then this 5-membered ring. Well, a 5-membered transition state isn't big enough for one atom to add to the top of the double bond and to stretch out and the other atom add to the bottom. 5 members isn't big enough. So now we know when we add a 4-membered ring that we add cis. Let's expand that and say now when we add a 5-membered ring, if we have a 5-membered ring transition state, the two groups will only add cis. And so that's what's happening. The 5-membered ring isn't big enough to add oxygen to one side and the other. It doesn't stretch that far. So we end up plopping the two oxygens on one side of the double bond. And then what happens is, then when the hydroxide comes in and strips the manganese off, you're left with two OHs cis. So the KMNO4 sets the oxygens cis in this mechanism. And we've kind of seen that before with the boron, with the mercury. It's those steps, those first steps, that set where the atoms are going. And then down here, it's kind of it kind of shows the model, sort of. Okay, so KMNO4 can only stretch enough to add to the same side. And guess what's going to happen with the osmium tetroxide? With the osmium tetroxide, there's an OS there, an OS there, OHs. So when we look at, there's two O's there. So when we look at the osmium tetroxide, it's the same kind of mechanism. You're going to go through a 5-member transition state to plop the two oxygens on the two carbons. You'll end up with a 5-membered osmium ring. In this case, the H2O2 comes in. It removes the osmium and puts two OHs there and reoxidizes the osmium back to osmium tetroxide. So in this reaction, what happens is that we use a lot of excess hydrogen peroxide, a little bit of osmium because it's super expensive, and so then we cycle the osmium back and forth as it adds to the double bond. But same general mechanism. So if you forget whether KMNO4 and osmium add 2 OHs cis, if you wrote the structures out, hopefully you'd be able to go, oh, 5-member transition state cis. Would you have to write this mechanism? Well, you're done writing mechanisms for the semester. Right, multiple choice. You have to deal with mechanisms, but not write them. We'll save that for next semester again. All right, everybody kind of with me? So, new reactions. Hydrogenation, 2 H's. There's no Markovnikov, anti-Markovnikov. 100% cis. Cis-Hydroxylations, as the name says, 2 OHs cis. No no Markovnikov. I think this is the last reaction. All right, so we've added things to double bonds. And my suggestion would be that if you can go through and actually create a table, or I guess individual flashcards, but you could create a table for every reaction that we've added something to the double bond, and you could make 3 columns. What did I add? How did I add it? And how did I add it? Like that. There you go. But if you don't have that column, or if you don't have that table, remember there are some rules about things that never add, or never can be regio, never can be stereoselective. Symmetry, no regioselectivity. Triangular intermediate, always trans. Square intermediate, always cis. 5-membered ring, which I can't do with my hands, but always cis. Anything with a carbocation, 50-50. And potentially regioselective. Right, so there's those rules that you can kind of remember about stereo and regioselectivity. Markovnikov and anti-Markovnikov are only a small subset. The ones we did last Monday, the ones that we did today, those reactions don't have a Markovnikov or an anti-Markovnikov. Now, last set of reactions have nothing to do with adding things to the double bond. The last set are oxidative cleavage. So I want to break the double bond apart. And there's several ways to do that. We can use either KMNO4, an acid, to do oxidative cleavage, or we can use ozone to do oxidative cleavage. Now notice the KMNO4 is back, bless you, but it's in a different acidity. So KMNO4 and hydroxide adds 2 OHs. KMNO4 and acid is going to end up cleaving the double bond. Ozone is going to end up cleaving the double bond. So that's why we call these oxidative cleavage. So the first thing is cleave the double bond. All right, great. So there's my double bond. I'm going to cleave it. So over here I'm going to write CH3, CH, and then I'll just write the CH3 down here. So all I did was erase the double bond. Cleave. What goes on the carbon now, since I cleaved the double bond? Well, there's a hint in the name. oxidative. So what should be attached to that carbon? If it's oxidative cleavage. An oxygen. What kind of oxygen? Well, a double bond. So what happens is that I cleave the double bond and I convert it to a carbonyl. That's the essence of oxidative cleavage. Cleave the double bond and turn each one of the carbons into a carbonyl. Okay? But there's a little bit of an issue that we have to deal with. And the issue that we have to deal with is this whole idea of oxidation. It turns out that there's a whole series of oxidations and reductions that you can do with carbonyls, particularly aldehydes. So an aldehyde is actually not oxidized into its highest oxidation state. The highest oxidation state of a carbonyl, well, is a carboxylic acid. So if you have an aldehyde in the presence of an oxidizing reagent, and we usually write those as an O in brackets, that means oxidizer, aldehydes can be easily oxidized to carboxylic acids. And next semester, we're going to talk about, well, primary alcohols can be oxidized to aldehydes onto carboxylic acids. So there's this series, this sort of series. This is the important one to remember, because I'm going to come back and we're going to determine whether an aldehyde stays an aldehyde after cleavage. And it will stay an aldehyde after cleavage if there's nothing there to oxidize it. If there's something there to oxidize it, the aldehyde becomes a carboxylic acid. Ketones? Ketones are stuck. Because once you have a ketone, you can't oxidize it any further. So if you tried to oxidize a ketone, you get no reaction. So ketones are in their highest oxidation state, but not aldehydes. Okay, so that becomes important for these reactions. And now let me give you the specific reagents that would oxidize an aldehyde up to a carboxylic acid. One would be CaMnO4. And the other would be hydrogen peroxide. And there's a bunch of others. There's a bunch of others. The others include things like oxygen gas and some other things. But these are the two that are most relevant now. So aldehydes will be oxidized to carboxylic acids in the presence of CaMnO4 or H2O2, because that's what they do. They're oxidizing reagents. Now, let me come back here. First step in writing the cleavage products is I cleave the double bond and I added 2 double bond O's. I look at this molecule. Let's say I'm doing this with CaMnO4 and H2 or H+. I look at this molecule right here. I see it's a carboxylic or let me start. I look at that. I see it's a ketone. Ketones in CaMnO4, nothing happens. So this is my final product for that piece. How about the other piece, though? For this molecule, what did I make? For the other piece, an aldehyde. What happens to an aldehyde with CaMnO4? It gets oxidized to a carboxylic acid. So the final product is that. So when we do our cleavage with KMNO4 and acid, we're going to erase the double bond, we're going to put in 2 carbonyls, we're going to check each piece. And when we check each piece, if it's a ketone, we're done. If it's an aldehyde, it's going to be oxidized to a carboxylic acid. So that's with KMNO4 and acid. Now, ozone has 2 potential reagents that can go with it. Hydrogen peroxide, and usually either zinc and hydrochloric acid or R2S. So there's actually 2 different ozone reactions I can do. I can do ozone with peroxide and ozone with R2HCl, or with zinc and HCl or R2S. How about ozone and hydrogen peroxide? What's it going to do? Well, this reagent is going to do exactly the same thing that the KMNO4 acid did. In other words, the ozone cleaves. We get 2 carbonyls. If you get an aldehyde, the aldehyde will react with the hydrogen peroxide to make the carboxylic acid. The ketone won't. Now, this set of reagents does not oxidize aldehydes. It doesn't oxidize any aldehydes. So once I do my cleavage, I'm done. If I made aldehydes, great. They're stuck as aldehydes. So there's 2 ways to do ozonolysis. And that is one where it oxidizes aldehydes, one where it doesn't. Again, giving us more versatile reactions. Now, the exact mechanisms for these you don't have to worry about. You just want to be able to write the products. All right, everybody kind of with me? So that's what this means. If you're using acidic KMNO4, you're going to make ketones and carboxylic acids because the aldehydes became carboxylic acids. If you use ozonolysis with hydrogen peroxide, you're going to do the same thing. If you use ozonolysis with R2S or zinc, HCl, you're going to make ketones and potentially aldehydes. There's one last piece, though, that needs to be dealt with. And that's this molecule on top. If I said, write the product of this, so let's write the product of this reaction with KMNO4 and acid, or ozone and H2O2, since they're going to give the same products. Let's follow my procedure. So my procedure was to split the double bond, erase the double bond, and replace it with a carbonyl. That's the cleavage part. Well, it's the oxidative cleavage part. And I would get that product. I would get those 2 products. Bottom product is this is a ketone. What happens to it? Nothing. It stays the same. Uh-oh. This has 2 aldehyde parts. That molecule's formaldehyde, right? That's what dead things are in, usually. Although they make plastics and other things out of it. How do we oxidize formaldehyde? It's not that bad. Each of the aldehyde parts, each of the hydrogens becomes an OH. So formaldehyde gets oxidized to this acid. And normally I would say, well, what is that acid called? And I normally have probably a cherry Diet Coke Zero in here. And I would say, let me take a sip of that acid. And you would say, oh, carbonic acid. So H2CO3 is carbonic acid. Carbonic acid's pretty unstable. And it decomposes to CO2 in water. So the formaldehyde part under KMNO4H plus or ozonolysis under peroxide will split the double bond. If it forms formaldehyde, that becomes CO2 in water. In the old days, when we had to try and figure out what the structure of a molecule was, and we knew we had a double bond, we could find out if the double bond occurred at the end of the molecule, because if I did an oxidative cleavage and it fizzed, that would tell me that the double bond occurred at the end of the molecule to give me formaldehyde and then carbonic acid. All right, so that's, I think, the end of the alkene reactions. And so you'll see alkynes, starting with naming, and some acid base for Wednesday. Oh, tests. Okay. Come and get these. Colleen. Grace. Alex. Anthony. Lauren. Carolyn. Andrew, Carolyn, Erica, Carolyn, Bianca, Kelly, Joe, Kelsey, Katie, Mary, Mary.